This tutorial will cover a couple examples using one-dimensional arrays. The first example is from section 12.8 in the course workbook, and the second exercise is from tutorial number 3, exercise 2. If you haven't already done so, please attempt those exercises and then check your solution. In today's tutorial session, we went over the strategy for writing the all-different function. One of the strategies that came up was that we take the first element in the array and compare it with all the following elements and make sure that it's not equal. Once we do that, we'll check from the second element, and then compare with all the remaining elements, and so on. And that's what this implementation is doing. The outer loop begins from 0 and it stops at size -1. The condition on the outer loop could be I less than size, but the last element has nothing to be compared with because nothing comes after it. That's why we're allowed to stop at size -1, less than size -1. The inner loop, on the other hand, starts from I plus 1, and that ensures that we only check elements that come afterwards, after the element that we're checking. And because we want to include the last element in the elements that we compare with, the condition for the inner loop is j less than size. And finally, the if condition is testing if two elements are the same, then we return false or 0 because they're not all different. At the end of the function, we'll return 1 because we only reach that point if we successfully completed all the loop iterations, which means that no elements were the same, so they were all different. The next question in the workbook is how many tests do you need to write to effectively test the all different function? And you could argue any number greater than or equal to 2, basically. You need at least one test which is not different and one test that is all different. In my test I have x full of 10 elements that are all different and y full of elements that has one repeated number which is 3. So to test that, when you call all different with x, the result should be true because they are all different. And when you call all different with y, the result should be false because there is a repeated number. And the if-else logic reflects that idea. The final exercise is to draw a memory diagram at point 1, and point 1 is just at the start of the all different function. In my test, that function gets called twice, so I'm drawing the diagram for the first time that it's called. So a good thing to check first is if there's anything stored on the static area, and there are some string literals in the printf statements, so I just indicated that with the test on the left hand side. Now on the stack we have two functions. Main calls all different, so there's two activation records. Main has no arguments, but it has two arrays as local variables, x and y. And when we draw those arrays, the largest address is the last element and the smallest is the first element. So for x, the element at index 0 has address 800, whereas the last element, which is x9, has address 836. So each integer requires 4 bytes, so the address is increased by 4 each time. I'm drawing the memory addresses, but it's not required here. I just added those for your benefit. This one I was using arrows, so it's not required to give the memory locations. And the activation record for all different has two arguments, x and size, and x inside of all different points to x in main. And what I mean by that is that it points to the first element of x. So x0, the address of x0 is stored inside of x in all different. And the size argument has value 10. At point 1, I and j, the local variables in all different, haven't been initialized. So that's the complete memory diagram at point 1. Now let's switch our focus to tutorial 3. The last remaining exercise is exercise 2. And this is a two-part question. We're asked to draw a memory diagram as well as to implement a function. So I'll implement the function first. We're asked to implement a function called allDominant, which takes two arrays and two integers. Notice that the first argument has a const in it, so reading from right to left, a is a pointer to an integer that is constant. That means that you can't change the value that a is pointing to. You can change the address that a stores, but you can't change the value at that address. It's declared const in this case because we aren't changing the arrays themselves. We're just seeing if one dominates the other. B should also be declared as const since that doesn't change either. The comments in the exercise give two promises for the function. The first one, that if m is greater than n, it returns -1, and that requirement is directly translated into code with if m greater than n, return -1. The second requirement is that if all the elements in A are greater than the corresponding elements in B, we return 1 or true. Otherwise, we return 0. I think the easiest way to do that is to loop over all the elements of both arrays. So I have the for loop going from I up to m-1. And at each step, I compare to see if bi is not less than ai, which is the same as bi greater or equal to ai. And if that's true, then b has a value that's greater than a, so a doesn't dominate b. So in that case, we return false or 0. And the last statement, return 1, if we successfully completed that loop, meaning all the elements in A are greater than the elements in B. The second part of the exercise is to draw a memory diagram the first time point 1 is reached, which is inside of a swap function that gets called from a sort function, which is called from main. You need to determine when swap first gets called. And that happens the first time that we go through the double for loop. So I has a value of 0 and j has a value of 1, because a0 is less than a1 initially. So the swap call does happen for I0 and J1. Now don't forget to swap the values inside the main X array. So now 889 is stored in the first element of X and 456 is stored in the second element. I've shown the diagram using memory addresses, but you could just as well use arrows for this example because it didn't specify which. And since I'm using memory addresses, you have to keep in mind that integers require 4 bytes, but pointers require 8 bytes. That's why if you look at the sort function, the arguments A, the address is 772, and the next address is 764. That leaves 8 bytes to store an 8-byte address. That is again because we're using 64-bit machines, not 32-bit machines. So addresses require 8 bytes or 64 bits. In this tutorial I covered 2 examples, and each had a memory diagram that was using arrays, and we also practiced writing functions that use arrays. Remember that when you pass an array as a function argument, it's the same thing as a pointer because the name of an array is just the address of the first element of the array. In coming presentations, you'll see more about higher dimensional arrays, so 2-dimensional arrays and even higher 3-dimensional arrays, as well as more connections between pointers and arrays.